Okay, we're going to start. If you want to, you can print this out. It should also be in your handout. Um, so having the full thing there might. Let's talk about lumen function. We've talked about body water. Um, it's important to think about the rumen as a container or a vessel of water. Um, it's a fairly large one. As we saw, it's a significant part of the body water, and we need to think about how that's managed and controlled. So when we're thinking about the rumen, what happens in the rumen is that solutes are removed from the ruminal solution and put over into the blood. And this is an active process. If we look at the um, sodium can fall down its concentration gradient through specific channels, or it might be exchanged with a protein enzyme carrier, sodium versus hydrogen ion. Sodium's going to move over to the blood side, and sodium's going to be pumped back in. This is the sodium potassium ATPase pump. It uses a significant amount of the energy in the body, and it's used to set up, because we have 3 pluses going out, 2 pluses going in, a difference in charge across membrane. We have potassium. It's going to drift out through channels onto the blood side. It won't go to the luminal side. So this is the inside of the rumen. This is the blood over here. Um, Potassium also can sneak between the cells. So if this represents two cells touching each other on the ruminal epithelium, so one cell here, one cell here, one cell here, sodium appears to have the ability to slip in those gaps. Chloride is going to be exchanged actively with bicarb. Chloride going in, bicarb going out. So these are transporters that are regulated uprated, downregulated as they are needed. So the more they're used, the more they're needed. We upregulate them as we absorb more and more VFA. We need to do that in conjunction with the electrolytes. So we upregulate those to help VFA absorption. Once chloride is inside the cell, it's going to fall out to the blood. So you can see that sodium is going to get to the blood, potassium is going to get to the blood, and chloride is going to get to the blood. So you're seeing an active process. Our VFAs are going to go in conjunction with these electrolytes. We have the ruminal epithelium taking solutes, moving them actively over to the blood side. So this is energy requirement, and there are regulators involved in that. So as we move them through, this becomes more hypotonic, and hopefully this maintains the isotonic as these things are moved and processed and recycled throughout the body. So when we think about the rumen, the forestomach of a cow, the rumen, reticulum, the omasum, and then the true stomach, the abomasum, we have a huge um, compartment here that is very well innervated. So you have all these grooves where the nerves travel along, and they um, set up and innervate the muscles of the body. This GI tract, this big forestomach. They also a huge blood supply to and from this. So we have blood from the heart coming, surrounding this with a bed of capillaries, and then those capillaries come together and they exit, the blood exits through the portal vein. We have a lot of complicated functioning. So this is eructation, the removal of gas. from the rumen. So the challenge with removing gas from the rumen is that you have an esophagus that is lower than the top of the rumen. So all these little dotted areas, I think they're calling them stippled, um, are where the gas accumulates. Gravity being what it is, the lighter things go to the top, the gas floats to the top, water floats down. So we have a specific sequence of events that takes this gas pocket and brings it down. So 6 seconds, 8 seconds, 13 seconds, brings it down in front of the esophagus. The uh, gases, mostly carbon dioxide and methane, are pushed out the esophagus and they are pushed out of the mouth in front of breathing. So as she starts to breathe out, this pocket is pushed out in front, and then the exhale from the lungs pushes out all those gases. So you're going to see that we've got the gases going to the esophagus, gases going to the esophagus, and we continue that cycle over and over again to help remove the gases. So one of the things that makes this work, you got a pattern of muscle contractions. The darker muscles are about to contract or just have contracted, is that the air bubble has to be where the body is expecting it, which means the rumen has to, ventral to dorsal, always has to have this part up on the dorsal side. If the cow lays down, the on her right side, the bubble moves here. The muscles will continue to do the pattern, but they won't be in the right location to push that air pocket out. So the air pocket is not where it's supposed to be. So one of the things that we need to have with a ruminant is the rumen always has to be oriented up and down relative to gravity. We need the air pocket at the top, the liquid on the bottom. We need to have things there. This is one of the problems a cow would have in space if the air doesn't have a specific place to go. No gravity is drawing it in one direction or forcing it in one direction or another. She could not eructate, no eructation, which means float, which means death. We also know that there's a sequence for mixing in our rumen. So you're looking at the flow of materials. We tend to have a flow that sort of goes this way, and that's why heavier objects end up in the reticulum, the RE. They keep getting forced in that direction. We have a flow coming from the reticulum back to the rumen, and all this mixing is also again dependent on gravity. So dorsal rumen, ventral rumen. You're looking at it from the side. You're looking at it from the top. We need gravity to be part of the process. So eructation, rumen contractions, they mix a whole lot better if the cow maintains what we call sternal recumbency or stands up, that her rumen is always straight up and down. That's why cows don't go over on their sides for extended periods of time. It alters the rumen function. The gases build up, make the cow uncomfortable. She'll sit up and start doing her normal eructation again. So when we're thinking, we've talked about electrolyte absorption. We also need to think about water in the rumen. Now, normally in the most places of the body, we have solute being removed, and then water follows that solute. So energy, um, pumps, systems, enzymes move the solutes around. Water follows passively, but not out of the rumen. So we have the ruminal lining moving electrolytes out, but water does not follow. So the rumen, as the solutes are removed, the water stays in place. The rumen becomes more and more hypotonic, which is what we want. We'll explain that as we. So we think about a cow. So here's our generic cow. We've got a happy little face here. We've got the rumen right here, and then the whole body surrounding that rumen. So we think about which way does water want to go. If we have the isotonic body at 290, and then we have the rumen at 260, solutes are removed, put in the blood, passed out in the urine, recycled through the salivary gland. We're constantly putting that. That makes um, this higher concentration of water than out here. So the natural inclination of water is to leave the rumen to go toward the blood. That's a bad idea, and we'll show you why in a minute. But it's a desire to move, but we have a barrier to water movement leaving the rumen. So we don't want the water to leave the rumen because we get huge fluctuations in the water pools. The natural direction, the natural desire of water is to go out of the rumen to flow toward the bloodstream down its concentration gradient from higher water in the rumen to lower water in the blood. The rumen is hypotonic. The blood is isotonic. So water is a higher concentration in the rumen, wants to move out, but the rumen is designed as a layer that prevents this movement. Why is that important? So if we think about where the water is, if we look at the rumen and we look at the plasma, you look at that they represent 13% and 8% of the body water, or 9 and 6% of the live weight. So these are fairly large pools. If we have stuff shifting back and forth, trying to even things out, we may have detriment or problems in maintaining the water pools and therefore the circulating um, fluids in the body. So what would happen if water were allowed to move? What would happen? The water would leave the rumen, and we generally dry out the rumen. And a dry rumen doesn't work nearly as well. We need to have that water stay in the rumen and allow things to be mixed and mushed around and absorbed, twisted, kneaded, all that stuff. So if water were allowed to leave, we'd have a lot of water going there. We'd have a big change in uh, blood volume. It would go up and down depending on where we are in the eating cycle, and that would be good for the cow adjusting to that. So we have this layer that prevents the movement of water and therefore keeps the water in the rumen and protects the blood volume outside. So if we think about the movement across the water, so rumen, we talked about water follows solute, but not in the rumen. So the rumen appears to have an appreciable barrier to net flux of water due to osmotic gradients normally present between the contents in the blood. So that's the epithelial lining has an appreciable barrier to water movement. Net daily movement, and this is in sheep, is thought to be from the rumen to the blood, but not a lot. Very little is believed to go from the blood to the rumen because that would be against the concentration gradient, and that's probably not going to happen. When the rumen is between 60 and 40, it's thought that very little or no net water movement occurs. So everything is kind of balanced, everybody stays in their own part of the body, each stays in their separate water compartment. Restricted more water movement is an exception in the GI tract. Normally, water follows solute anywhere in the digestive tract, just not in the rumen and reticulum. And that change in blood volume, the water moving in and out of the rumen, drying out the rumen, filling up the blood pool is the reason for that. We don't want that to happen.